right, great. Well, thank you guys all for coming early in the morning. Today I'm going to start off the volcano session with trying to give sort of a global perspective of what we've learned about volcanic systems through geodesy primarily, although we're very, of course, interested in other techniques too. So just as a sort of a motivation for our study and our session, is just to understand of looking at how many different volcanoes have we been able to study deformation at as a function of time. And we've really just had an explosion in our ability to do this thanks to satellite observations, in particular satellite INSAR. And what this means is that we are able to study a lot more volcanoes than in the past, where we may only have had detailed studies at a few dozen. We now can do hundreds. We can now do all volcanoes everywhere. But we still have an age-old question, which is when is this deformation that we're seeing a hazard and when not? And so there's a lot of work that we can do in terms of synthesizing the observations that we have, as well as using modeling techniques that we'll hear later about in the session. And another key point I want to emphasize is using this data with end users, the volcano observatories that exist around the world. There are more than 100 volcano observatories around the world. These are the people that need to use this data to inform decision makers, and that's who we need to work very closely with. All right, so just to acknowledge this is sort of a summary of a lot of different projects that we've been working on to try to help answer this question on a global basis, involving lots of people. There's a variety of projects I'll talk about throughout here. I'll just mention Mike Poland, who was just mentioned as sort of a co-PI on this project funded by the USGS Powell Center for Synthesis and Analysis out of Fort Collins. I'm glad to talk to anybody about this type of a project. It's very helpful for sort of bringing people together to talk about different perspectives, in this case of advancing satellite studies of volcanoes, as well as Juliet Biggs, who I'll talk about, who's involved in several of these other projects. So my plan of attack today is to try to walk you through a line of reasoning to get you to a call to action at the end. So my line of attack is to talk about that monitoring data does in fact improve our understanding of forecasts of eruptions. It doesn't always do that, and it's important to ask the question. Of course, you might say, no duh, monitoring data helps, but we can start to quantify a little bit better of when it's useful, when it's not, how much monitoring data, and so forth. And that's still an active area of research. But a key problem, of course, is that a lot of volcanoes do not have ground-based monitoring data. And I'll show you some statistics about that. Satellite data can fill some of the gaps. It can't fill all the gaps, but it can help, and we could do a better job of exploiting that data. I'll argue that we currently have 10 SAR satellites in orbit, and we are not fully exploiting them for this problem of volcano observations. And we need to, as we prepare for the upcoming NASA ISRO NISAR mission that will include really a global comprehensive study, we need to be able to use the full constellation. That one satellite mission is not going to be enough. We can really gain some synergies from using them all together. All right. So let me just start with a paper I really like by Winson et al. That's a question of how useful is monitoring data. And this is ground-based monitoring data. And they tried to do just a simple study of looking at about 200 eruptions at different volcanoes and trying to understand, here's the red lines are eruptions, and these are showing volcano alert levels of, do we see unrest? Do we issue an alert? Is that alert timely in terms of warning of the eruption? Is it totally missing the eruption? And under what categories are we able to make successful forecasts or not? And they did a nice study of showing this value here as a function of monitoring. So what you're seeing here is those missed ones. When did we completely not issue an alert related to an eruption? When did we have one that was pretty useful or one that was not quite useful, either premature or too late? And one important result of this paper is that as you increase the amount of ground-based monitoring, going from basically volcanoes with no monitoring to places with very extensive networks, your amount of green here is increasing. Right? This is just evidence that increased monitoring helps you better assess what's happening at a volcano and making a forecast. So this is just showing you that increased monitoring is good, but also just realizing that there's still a big red zone here. There's still a lot of eruptions that are missed for various reasons, either because the monitoring still was not complete, or there were just certain volcanoes and certain types of eruptions that don't give us signals that we can yet interpret. So this is sort of two things. 2 points from this slide. One is that increased monitoring does help us improve forecasts. One is that even with extensive ground-based networks, we have room for improvement. So that's showing the utility of ground-based data, but a lot of volcanoes are not monitored, including especially high-risk volcanoes. So there have been recent projects that have been organized through the global volcano model to just quantify on a global basis, where are volcanoes that are not monitored, where are these volcanoes that are high risk. So they've come up with a statistic that only 35% of volcanoes that have erupted since the year 1500 are continuously monitored. So that means there's a lot of volcanoes out there that have had eruptions in the last 500 years that are not being monitored. And in particular, a lot of these volcanoes are in areas with large population density. So here's another compilation here, just showing again a list of monitoring levels, showing different risk levels of these volcanoes, showing there's a lot of volcanoes in several highly populated areas that have a high risk level and no effective ground monitoring. So this is just showing a call for action that we, of course, need more ground monitoring, but there are, of course, logistical and financial implications of that. We already have a constellation of satellites in orbit. To what extent can they help to fill in some of these gaps? So let me just talk about how satellite data can be useful even in areas where we have extensive ground-based monitoring. So there's a nice recent paper by Susie Ebmeyer that sort of summarizes a couple of examples. Here's just a couple of volcanoes that are fairly well monitored on the ground, and satellite data are still useful. So here's Arenal in Costa Rica showing the ground-based network, and this area in gray is showing the area that was found to be deforming. So there's basically a road here, and instruments are along the road, and you're able to see a more synoptic view with the satellite data. At Tungurahua in Ecuador, there's also a very nice ground-based network, but there's one area where there are no stations, I think primarily for safety reasons and frequent eruptions, that was found to be deforming. So these are sort of showing the complementarity of these two techniques. Another good example recently is at Nevado del Ruiz. Nevado del Ruiz is right here, and a recent area of deformation was found by the GPS network, which is located here on the volcano. All the stations were sort of moving in the same direction. It's hard to interpret what that meant, but with a synoptic view of INSAR, you could see that, in fact, yes, there was a very large-scale deformation signal that was much bigger than the volcano itself. So a lot of monitoring networks at volcanoes are restricted to the edifice itself, and the synoptic view can give you a more wide-ranging view than you would see from just the ground network. As well as, in addition to volcanoes that are not erupted at all. So there's a new term that was invented by a headline writer called zombie volcano, and a zombie volcano has entered popular language as either volcanoes that erupt zombies, volcanoes that or zombies that get their power from volcanoes, but in this case, what is meant is volcanoes that have either had no historical eruptions or no eruptions in hundreds of thousands of years that are still showing some signs of activity. And this is important because Sir Stephen Sparks has made an observation that every 2 years or so a volcano erupts that has no historic eruptions. So we frequently see eruptions at volcanoes that are not instrumented because they were not thought to be a threat. Looking at where we are now and where we're going to be in the future is we have a growing constellation of INSAR satellites. A lot of this data is available through UNAVCO. A lot of this legacy data is openly available. We're focusing on data that's available right now and in the near future. As I said, there are currently 10 SAR satellites in orbit, and there will be more coming in the next 2 or 3 years. And each of these satellites has different advantage, strengths, and limitations in terms of monitoring volcanoes. They have different spatial resolutions, different temporal resolutions, different wavelengths of the SAR. And this has important implications for the quality of deformation observations we're able to make. So this is just one example of showing data from a couple of different satellites, from RadarSat-2, from Sentinel, and from ALOS-2 at a volcano in southern Chile, Cordoncalli volcano that had a recent eruption in 2011, has been uplifting at a rate of 45 centimeters per year after the eruption, and sort of a complicated eruption pattern. So what we're seeing here is here's where the last eruption happened in 2011. Here are 2 other volcanoes that are associated with this sort of Graben feature, where the eruptions have occurred and where the ground deformation is occurring. And so the point here is that Sentinel data is a fantastic tool. It is globally available. It is C-band. But it doesn't work well at every single volcano, especially depending on the background mission and the vegetation. So I could give you several other examples. In this case, this is a highly vegetated area that has a lot of snowfall. Sentinel observations are typically made every 12 days at best, and those observations are not sufficient to be able to maintain coherence in the vegetated areas around the bare lava flows basically at this volcano. So this is just showing you a comparison of sentinel data, in this case spanning the Austral winter. That's sort of very restricted. You can't really tell if there's deformation happening in the areas surrounding you. But similar time period data at L-band is able to really reveal what's happening surrounding the volcano. And even C-band data from RadarSat-2 that has a higher bandwidth or higher spatial resolution is more coherent over similar time intervals. So this is just trying to make the case that yes, Sentinel is a great tool, but there are highly vegetated areas in Central America and Africa and Papua New Guinea and southern Chile where the Sentinel data are not sufficient. There really is a role to be played from these otherwise what we would call restricted data satellites without an open data policy. All right, so where do we go next? So let me just try to outline a couple of the problems I see what we have right now and how we can try to improve them. One is that we aren't always getting the satellite data we need at every volcano. So how can we do better with that? We need better tools to interpret the data we have, and that includes both developing better modeling tools that will be the subject of some of the future talks, but I'll also talk about trying to create databases of past activity that could be used to be compared with deformation that's being observed at a new volcano. And then I also try to mention a little bit about effective science communication, primarily with working with volcano observatories. All right, so one thing that we are working on, and we're glad to take input on, is as part of the Powell Center, is trying to develop an observing strategy for the 1,400 or so Holocene volcanoes around the world. Just basically looking at all these different volcanoes, what is their level of activity? Have they had eruptions in the last 20 years? Have they had evidence of satellite-detected unrest? As I mentioned, we have about 230 volcanoes that have ground deformation detected by space. If you add in thermal sensors and degassing sensors, that number comes up to about 330. There are 330 volcanoes that have had some unrest detected at them from space. And so we sort of have classified these in terms of their level of activity and how frequently their eruptions are occurring. And so have sort of made a preliminary list, and I'm glad to share this list if people want to make comments, of how many volcanoes we really need to have weekly observations at or monthly, and how many do we need to have just some sort of background mission to monitor any changes in the level of the volcano. And then our goal is to communicate this with the space agencies to develop a plan and quotas for data from the different satellites that are currently in orbit to be able to acquire the data we need in the right places. The other thing that I think is extremely useful is to have easily accessible information on past episodes of deformation at a given volcano and globally to be able to look for trends. As I said, there's in the past we've relied on a handful of volcanoes that we sort of say, how is the type of activity I'm seeing at my volcano under study similar to the volcanoes that we have studied, whether it be Kilauea or Etna or Sakurajima or whatever. But maybe those are not the best analogs for the particular volcano I'm looking at. Maybe there's a volcano that is very similar in terms of its behavior to one that we're studying, but hasn't had this long record of activity. So how can we get access to that data? And right now there are a variety of different databases that are all working with each other with slightly different purposes. But I'll just focus here first on the Smithsonian Institution Global Volcano Program, where they have now, if you go look up any different volcano in the system, they've now added a tab which says deformation history as well as eruptive history. There's now an emission history and bulletin reports and all these sort of other things that we as a community need to update. So the goal here is to be able to communicate to the wider volcanology community what do we know about deformation at this volcano, primarily relying on peer-reviewed papers to be able to get that information more widely known. And then the raw data that's available here is also being made available through WOVODET. That's the World Organization of Volcano Observatories, which has a database program where they're trying to compile observations at a variety of volcanoes for people to do this sort of thing. And then the Comet Group in the UK is also doing a project where they're making a database of the most recent Sentinel interferograms available. All right, so let me just give you a clue. How are these databases useful? So this is just a compilation of what we've done in terms of volcano deformation events at volcanoes that was compiled a couple of years ago, just looking at the duration of these deformation events and the magnitude of those events, and whether those deformation events were related to eruption or not to eruption. And so you can sort of see there's a little bit of a trend here that episodes that have large magnitude usually have shorter duration, but probably we are very undersampled in this area of short duration events. But in the area that may be a little bit better studied, we can see that there's no simple relationship between which ones resulted in eruption and which ones didn't. But if you sort of aggregate these together in terms of the percent that eruption, you can see that events that are longer lived usually are less likely to erupt, to result in eruption, and events that have higher magnitudes are more likely to erupt. And so you could break this down by composition of volcano and so forth, but there's still a lot of work that can be done in exploring these databases. All right, so let me just try to end by talking about the communication aspects of this. I think we had some great talks about communicating science. Communicating with, about volcanoes and potential volcanic eruptions is a slightly different beast because we rely on volcano observatories in all these different countries to actually keep track of what is happening at their volcanoes and reporting that information to their governments. And so what we really would like to do is encourage these volcano observatories to be able to use satellite data in their routine analysis. And so various programs are trying to build capacity of volcano observatories to do this. And so just as an example, one of my students will have a poster that talks about what we call the CEOS Latin American Volcano Pilot Project, where a bunch of different space agencies and the Committee on Earth Observing Satellites had a project for 3 years where they said, let's open up a bunch of data availability, and we're going to ask you to, a bunch of data providers to add value to that data and communicate with volcano observatories throughout Latin America, and then we'll assess at the end of this project how useful was this data for those volcano observatories. And so just to cut to the chase, we submitted surveys to about 10 different volcano observatories throughout Latin America, asking them how the data was used, what could be done to improve data availability in these areas. And I think we were surprised by the variety of responses. It's a very heterogeneous group in terms of the capabilities at these volcano observatories. Some volcano observatories want raw satellite data, others want data that's interpreted. Some volcanoes have no functioning volcano observatory at them, and so that's a special case to be thought of. I think another important thing is the training and capacity building is an important aspect of this, is developing long-term relationships with these observatories to help them interpret the data that they're getting and understand how to integrate it with the rest of their data streams. And to that end, I want to point people's attention to this nice paper that's a little dated now by Chris Newhall from the UNAVCO Subcommission on Crisis Protocols, sort of about when people find deformation at volcanoes, what is the protocol? And so I often get media requests about, oh, we see unrest happening at such and so volcano, can you comment on them? And I send them this paragraph from Chris's paper, which basically says some warnings and forecasts, especially those from remote sensing data, have ignored important constraints from other disciplines. Some are from scientists unable to resist the siren call of media exposure. That's the one I think that is important to send out to the media. And many are innocent media-solicited forecasts. Whatever the cause, the effects are serious distraction from more pressing duties. And so the point here I'm trying to raise is that developing these communications with volcano observatories is absolutely essential, that these are the first people that we should be communicating with, and this is going to be more and more difficult as we go forward to the future into an era of Twitter and open data. So just to show an example of a gung, which will be talked about by Heather a little bit more later in terms of what happened at this volcano, is somebody can process Sentinel data and say, hey, look, is there some sort of deformation happening at this volcano that has not been vetted at all by a volcano observatory in terms of interpreting that in terms of tilt data that might exist on the ground. And so other people go on Twitter to say that this is not deformation, that we think that this is atmospheric effects. And so I think in terms of going forward, Twitter is a great tool, but we need to develop some new protocols, updating Chris Newhall's UNAVCO commission to really think about how do we communicate observations of volcano deformation with the public and with volcano observatories in the future. All right, so let me end there by just sort of summarizing that I think monitoring data, in particular satellite data, can be very useful in these crises. Again, it's not going to solve all of the problems. There will be some volcanic eruptions that happen without precursors we can detect from satellites because of the low repeat intervals and so forth, but we can do a lot better than we're doing today. And so I think if there's a call to action for us to work with space agencies to get the right data at the right volcanoes, to get that data that we already have in hand into databases that are more useful for anybody who's trying to study hazards, and then improving the uptake of these satellite data with volcano observatories really requires sort of scientific diplomacy and work as both a global community and sort of individual scientists working with volcano observatories. So with that, I'll take any questions you have. Thank you.
So when it comes to, is it on?
It's on.
To earthquake hazard, right? One effort right now, and it's very simple and basic and statistical, is operational earthquake forecasting, just updating time-dependent hazard based on relatively well understood statistics. Do you see something like that in the future of volcano studies, if we have these data sets to have a relatively hands-off approach rather than individuals making their personal opinions or forecasts?
That's a great question. I think so. I think there's probably going to be a lot of discussion of that question, Roland. I guess my original statement would be, during a volcanic crisis that's often rapidly evolving, that there's a need for immediate information before it goes into any complicated model. So a single interferogram or a single SAR image can have a huge impact on evacuation. So I think the greatest example is Merapi. In 2010, during its eruption, a single SAR image combined with ground-based data saved tens of thousands of lives in terms of knowing what the volcanic dome was going to do. And so it's sort of so that single image combined with a bunch of data in somebody's head, indicated that. Now, to the extent that which we can automate that in terms of developing a time-dependent volcanic hazard, I think is an open question for research. I'm not convinced we're there yet.
Another question? I have one for you. 1,400 volcanoes on our planet, and you say we can do global geodesy or observations at these volcanoes. How many of these are actually poorly accessible by INSAR? I mean, some are below ice, actually quite a high number of them, or thick vegetation. In reality, can we observe all of these volcanoes with INSAR?
That's a great question. So the answer is no, of course, Reistein. There are some volcanoes that are going to be very difficult for all the reasons that you just mentioned. But I would point to an example, for example, of Villarrica volcano in Chile, which has a permanent glacier on the summit, and so and also has an active lava lake within it. And so there's some things at Villarrica we're not going to be able to answer. We're not going to be able to really see conduit level processes because we can't see right up next to the conduit. But at Villarrica, for example, the vegetation and glacier don't cover everything, and we can actually see, for example, at Villarrica that there is inflation that's seen offset from the summit. And so I think that we should do a compilation of how many volcanoes, even within 10 kilometers, we completely fail. But even if an observation is not right on the edifice itself, it still can be very useful. And so I didn't, in fact, mention that, but in Susie Ebmeyer's paper, she talks about how something on the order of 10 to 20% of volcanic deformation events are happening some 5 to 10 or more kilometers away from a volcano. So even if the volcano itself is difficult for INSAR to study, there's still value in seeing the synoptic view around it.
Okay. Maybe I have one more question. I wasn't quite aware of that study that showed all the amount of monitoring, but how much of that monitoring was geodetic monitoring?
Very little. I mean, I think it, and so it has. I have to go back and look at the thing to see how they've broken it down. I think that there's still sort of a gap in terms of really understanding which volcanoes have which sensors on them. Primarily, the default sensor is a seismometer or a small network of seismometers. And so ground-based geodetic observations, I don't think there's a simple number of what percentage of these volcanoes have it, but I think, I mentioned that 35% have some sort of continuous monitoring, and I would guess that only a small fraction of that is actually geodetic continuous monitoring. All right, thanks.